Hello, in this screencast we're going to walk through the idea of what is called a confidence interval, and it's highlighted in chapter 12 of our text. In the previous chapters, we took a look at what was called the central limit theorem, which basically says that for most any set of data, that the um, distribution of the sample means is going to be approximately normal, and it would be centered about whatever that mean was of the population and have a spread defined by what was called the standard error. And here we have the formula for standard error, which was the standard deviation divided by the square root of the sample size. And we had an example a number of times where we took a look at um, the idea of if the population of students taking the SAT had a mean of 500 and a standard deviation of 100, uh, how would the curve or the distribution of all of the possible samples of sample size 400 look like? And that's what this normal distribution is giving us a diagram of here. And how we set this up, if you recall, was this. Um, on the black colored markings here is for the actual z-score. The z-score of 0 means that you're at the mean. And then each increment going up is a positive 1, 2, 3 z-scores, and a negative 1, 2, and 3 z-score going to the left. And in purple here are the values that represent for this context here, where we had a mean of 500, and the standard deviation of the actual population is 100. But what we're doing here is this distribution is not of individual scores. It is the distribution of the averages of groups of 400. So it's a very different distribution here, and it's a much more tighter group. And the tightness or the deviation of each of these z-scores is dictated by what's called a standard error. So we took the 100, which was the standard deviation of the population individual scores, and we divided it by the square root of 400, 400 being the sample size in this example that I just created. And that gave us a standard error of 5. So each one of these z-score increments has a value of 5 as far as the context of SAT scores. So in purple, we have the values of the SAT scores fitting on this normal curve. And again, this is the distribution of the sample means, not of individual scores. So the average of all the averages is going to be 500. But each one of these increments is worth 5 points. Again, the standard error. So you see 505, 510, 515. And what this distribution is basically standing for is that if we continuously took samples of size 400 and we took the average of those 400 students, the average SAT scores of those 400 students, and we plotted them on here, most of them are going to fall within 10 points of the mean, up to 510 and down to 490. Few of them are going to end up in this tail or this section of the curve, and a few of them are going to end up down here. And if you recall, we had some problems where we had to find what between what two values are 95% of the average is going to fall. And we found that 95% due to a z-score of 1.96. We looked in the back of the book in the area under the curve, and if 95% is this inner interval here, then this upper tail is going to be 2.5%, and this lower tail is going to be 2.5%. And we found where is the area under the curve from a certain point to the mean of 47.5%. So the 0.4750 yielded a z-score of 1.96. So we had problems where we found an interval such that 95% of the time we can expect that if we take a random sample of 400 students nationally, we can expect to get an average of those 400 students to be within 1.96 z-scores or 1.96 of these standard errors. So we had to multiply the z-score of 1.96 times the standard error. And again, in this case, the standard error came from this formula, which gave us 9.8. And we added 9.8 to the mean, and we subtracted 9.8 from the mean to get an interval from 509.8 down to 490.2. Which again means that if we randomly select groups of 400 and we took a sample mean of that group of 400, 95% of the time we're going to get an average between 490.2 and 509.8. And that again is if we already know what the mean is. The shift we're going to make now in this chapter to confidence intervals is this. What if we don't know what the actual mean is? And what we are doing is then instead taking a random sample of 400 students, and we're going to use that random sample to make our best estimate of what the actual population mean is. So in blue here I have what we're going to be working on now for this chapter and basically from here on in. We don't know what the population mean is, which is the whole point of us doing this study now. For the purposes of this problem in this chapter, we're actually giving you what the population standard deviation is just to get through the process. Next chapter, we're going to see what we do if we actually don't have this. But for now, walking through this, we have the idea now again where we don't know what the actual population mean is. We're going to take a random sample of 400 students again, and we're going to get a sample mean. And let's just say, for example, that sample mean ends up being, 505. And we'll come back to that in a second. So that 505 is going to be our what's called our best point estimate. That's what that stands for. That is our best point estimate. That's all we have to go on. But we realize that most likely the true population mean is not going to be exactly 505, but it's going to be close. So what we need to do is we need to give ourselves a margin of error. We need to give ourselves a little wiggle room here that we say that, all right, for example, I know that my sample of 400 students has a mean of 505. And right now that's the best thing I have going for me. But if I add and subtract some values to it, then I might be more sure that the actual population mean is going to be within that range. And what we're going to do is basically use the same process we did up here to find this 95% interval and apply it to our sample mean that we got of our 400. This is called a confidence interval. And the 95%, just like alpha in the last chapter, 0.05 was our customary value for alpha. 95% is going to be our customary level of confidence. And they're synonymous with each other. This could change to 99, it could be down to 90. And the chapter talks through that. But for this process, we're going to stick with what's called a 95% confidence interval. And what that does is that gives us an idea of how big of a margin of error we are going to apply to this 505 point estimate that we have. So let's walk through the process. We take 505, which is what our point estimate is, and again that's our best single estimate because that's all we have. We have 505 as the average of our 400 students we selected. We're going to add and subtract to that a margin of error. And that margin of error is the same process that we used up here. The 95% dictates to us what our z-score is going to be, 1.96. And our standard error is based on two things. It's based on the standard deviation, which was 100. We're borrowing that from here. Again, next chapter, we're going to take a look at what do we do if we don't have this. And the sample size. And the sample size, for the purposes of this problem, we're going to keep it at 400. So 100 divided by the square root of 400 ends up giving us a standard error of 5. So these two things dictate to us what's the margin of error. In this case here, when I'm using the same values, it's 9.8. So we're going to take 505, which is our best guess. That's the sample mean that we have. And we're going to add to that 9.8, and we're going to subtract from it 9.8. And it's going to give us the same interval that we have here. But instead of being centered at 500, it's being centered here at 505. Okay, so this same bar right here, we're going to take and we're going to apply it to this. We're going to add to it 9.8 points, and we're going to subtract from it 9.8 points. And remember now, the actual population mean is unknown. So we're going to put a little marker here to indicate where that is. All right. And in the blue here is our confidence interval. And it's down to, from this value, again, 9.8 points away, which gives us down to 495.2. And it reaches all the way up to 9.8 points above the 505, which is at 514.9. So this is our confidence interval. That's what that's called. A lot of times in TV, you'll see this point estimate and a little plus or minus in the corner for the margin of error. A confidence interval is written in interval notation, which you take a parentheses, and then you have the lower end, and then a comma, and then the upper end, and then parentheses again. But again, a lot of times in television and in commercials and any type of posters, for example, it might be seen as the value of your actual sample mean and then plus or minus a margin of error. But again, if they ask you for the confidence interval itself, then it's in this format right here. And you'll see then, and again, understand that we're going through a process of trying to guess our best guess, or an educated guess, which is basically what statistics is, of what the actual population mean is. Now, how does that work? What does that mean to us? Well, if we follow the same process right here of taking that margin of error and we add or subtract it to any one of our sample means, no matter where we fall here, we take this same interval, again, up 9.8 points and down 9.8 points from whatever we get. And if we plot it, and as long as we get a sample mean within this window here, then our interval is going to spread to where we actually do encompass the true mean. So we can be confident 95% of the time, and again that goes back to this 95% interval, 95% of the time you're going to get a sample mean within this window. If we apply this margin of error to that sample mean that we get, then that new margin of error is going to encompass what the true mean is right here to be understood. 5% of the time, you're going to get a sample mean outside this window here. And if, for example, if it fell outside this window, and I'll do that in a different color right now, in orange, if we ended up, for example, a mean out here, and we applied the same margin of error of going down 9.8 points and going up 9.8 points, it's not going to reach far enough. And in this case here, it's not going to encompass the true mean. All right. So that's basically how you do this. It's taking a lot of the same information and process we had before, but flipping it around. And again, what we're doing is we're taking a point estimate and we're adding and subtracting a margin error to that to help make our estimate more likely to be true.